Okay, hey everybody, time for the next session. So next up we have Mark Jessup. Many of you would have seen Mark speak last year at the MiniConf, and of course many of you will remember Tux in Space, the awesome video that was shown at the dinner last year. So that was another one of Mark's projects. So everybody make Mark welcome. Thank you.
Just checking it's all working. Yep. So my name is Mark Jessup. I'm a electronic engineering PhD student at the University of Adelaide. So this whole story kind of starts about June last year, where my supervisor, who was in the UK, just because he goes there every summer, he sent me an email and said, "Do you want to come to the UK and work on a CubeSat?" And of course I'd said yes, because I'd be an idiot to say no. And 2 weeks later, I was at the University of Bath in the UK and working with Tellini, Jay Wardina, Catherine Mitchell, Robert Watson and Julian Rose on a CubeSat. So my role was mainly PCB design and also quite a lot of software work. So to start off with, what is a CubeSat? Well, it's just what it sounds like. It's a satellite that's a cube. The standard form factor is 10 by 10 by 10 centimetres, so 10 centimetres cubed, though you can get larger versions as well, and they're usually multiples of the standard form factor, which is referred to as 1U, so you could have 2U or a 3U CubeSat, sometimes even bigger. So the main point of a CubeSat is that it's cheap. For a couple $100,000, you too can launch your experiment into space and have it stay up there for a couple of years. The cheapness is mainly because they're launched in batches. So a standard launch might have 10 or 20 CubeSats on it. This, of course, can make it quite cheap. Another advantage is a relatively short development cycle. So in the case of topcat, which I'll get to shortly, we went from concept to working prototype in about 2 months, and it's being launched this year. So it's being launched later on this year. So you can also get a CubeSat kit, which means you could make your own CubeSat, and the kit would contain, for example, the downlink telemetry and also uplink. So that part of it can be already done for you. So the CubeSat that I was involved in is UCube-1. It's a 3U CubeSat funded by the UK Space Agency. And the main development was by a company called ClydeSpace, who are a division of Strathclyde University in the UK. So there's 5 payloads, topcat's one amongst many. So we've got FunCube. So FunCube is an amateur radio repeater by a group called AMSAT. They've made a lot of ham radio satellites, and in a UCube, FunCube is going to be an amateur radio repeater. It also acts as a backup telemetry system. So if the main telemetry system fails, we do have backups, kind of. I'll get to that later. There's My Pocket Cube. There's a very weird spelling of cube, but anyway. This has a few different sensors in it, a few different experiments. There's opportunity for hobbyists to run code on this payload. I really hope they have good sandboxing, because if they don't, there's going to be problems. But it's a really cool experiment, and you can look it up online and find out how to get involved with that. From Astrium, who is actually a professional satellite development company, there's Janus. So this is a Vertex 4 FPGA. It's part rad-hardened, part not. So in the rad-hardened part, they're running all their critical code. In the non-rad-hardened part, they're doing some experiments. So they want to see how radiation from space will affect an FPGA. And what they're doing is they're making a random number generator. So they're using cosmic rays which hit the FPGA, and I'm not sure exactly how they're doing it, but they're using it to generate random numbers. There's a CMOS imager test, which is testing a new CMOS imaging substrate. I'm not sure exactly how that works, but the idea is, will it work well in a space environment? And finally, there's topcat, which is the project that I worked on. So the aim of topcat is to collect information, mainly in the form of electron density measurements, on the upper ionosphere and the plasmasphere. So for those that don't know about the ionosphere, it's a number of layers of ionized particles ranging altitudes from about 50 to 400 kilometers above the surface of the Earth. And the ionosphere affects radio waves traveling through it, affects all radio waves traveling through it to some degree. For example, the majority of your positioning error in your handheld GPS devices is due to the ionosphere, and work's being done to make these more accurate. So we can quantify the state of the ionosphere by using electron density measurements. So we state the number of free electrons per cubic meter, and from this we can work out various properties, for example refractivity, what it will do to radio waves traveling through it. Above the ionosphere is the plasmasphere, which is a similar layer but weaker and doesn't have as much of an effect. So the whole point of topcat is to understand more about the ionosphere. So these measurements that we take will be incorporated into existing models using a process called tomography, and eventually we'll be able to develop new, better models. So how do we do this? So the key principle is that radio waves travelling through the ionosphere are delayed slightly dependent on their frequency and also dependent on the electron density along the radio path. So we can, using a transmitter which has broadcasting on two frequencies, we can measure the phase difference between the two signals, and we can, working backwards using a lot of really complicated mathematics and lots of measurements, we can eventually figure out what the electron density is, and this can be built up into a useful map, for example. So the hardware we use to do this, the core of topcat is a Novatel dual frequency GPS receiver. It's one of the smallest dual frequency receivers on the market, or commercial market anyway. I'm sure they're smaller for the military. And the receiver that we're flying is space rated. It doesn't quite mean what you might think it means. I'll get to that in a minute. So to handle communication between the GPS and the rest of the CubeSat platform, which is what I'll be referring to as through the rest of the talk, we're using an ATmega 256. Now you've probably all heard of these. It's the same chip which is inside the Arduino Mega. And we mainly picked it because of its huge amount of RAM, and I'll get to why we need that later on. For long-term storage, we use a 1 megabit EEPROM. Yes, we could have used a flash. The choice of EEPROM, I can't remember the exact reason it was chosen now. That was slightly before I joined the project, and there was some good reason behind it. It was to do with how it handles radiation environments. But anyway. So we actually got two GPS receivers for this project. One for testing on the ground and one to go into the CubeSat. They're about 4,000 pounds each. One's space rated and one isn't. So what's the difference between the two? So you may or may not know, I know Badale knows this, all GPS units have built-in limitations. The test string is pretty much if velocity greater than 500 meters per second, and if altitude is greater than 18 kilometers, drop GPS lock. Does anyone know why that would be the case? Or missiles. Exactly. There's one other situation in which this condition is satisfied, and that's on a satellite. So we had to get a GPS which would maintain lock going at ridiculous speeds, for example 10 kilometers per second, which is what this CubeSat is going to be orbiting at. To get one of these, it required a heck of a lot of paperwork. You have to deal with the US State Department and get permission to basically get one out of the US. We launched him from Kazakhstan. Even more paperwork. It's wonderful. So in the end, the cost difference between the space-rated version and the non-space-rated version was £200. That was because it's a one-line code change, and they had to reprogram the GPS module, which apparently cost £200. So that's how it works out. Now, we got this lovely space-rated module, and we don't actually know whether it's space-rated. We just taken Novatel's word for this. So we figured we'd better test this out. Now, the main reason for testing it is, yes, if our payload fails, that sucks for us. Our GPS is also being used for the main positioning for the CubeSat. So that's how they're working out the initial orbit. If our GPS goes down or doesn't maintain a lock once it's in orbit, big problems. So I got to use this device here, which you can kind of see. It's called a CAST 1000 GPS simulator. You program in a path or a set of paths, and it will generate fake GPS signals which fool a GPS receiver into thinking it's in a certain location or moving at a certain speed, for example. If you've been following the news lately, you would have seen how the Iranians claimed to take down a US UAV. They claimed to fool its GPS. This is the kind of thing they would have been using, though probably a much more expensive version, a much more sophisticated version. It was also quite good at making my phone think it was at the South Pole. And that led to some very interesting Google Latitude updates. So that was quite fun. And anyway, we got it to, we proved the GPS actually did work at the high altitudes and the high speeds, so that was good enough. So the software, what does the payload have to do? Well, the basic requirements are it has to pass binary data from the GPS. The Novatel GPS only speaks binary. Actually, it can speak NMEA, but we're not interested in that. So the information we're interested in includes position, of course, time, and phase measurements, also known as pseudoranges, and there's also a couple of other different values that are required as well. We package the data into 256 byte packets, and we store them into our EEPROM for long-term storage. By that I mean like a couple of hours. We don't want to keep them in RAM. And we also have to respond to I2C commands from the CubeSat platform. We have to respond to these commands within 2 milliseconds. Now that seems to be a pretty long time. There's a few reasons why this can be annoying. Anyway, if we miss our timing deadlines 3 times in a row, the platform assumes we've had a failure and shuts us down. So it's very important not to miss those timing deadlines. And finally, we have data transfer. So we tell the payload we have X many packets to send. We can assign certain priority levels for reasons that I'll get into a little bit later on. And the payload on the platform will say, okay, give us some data now, and it will add it into the downlink buffer, and eventually it will get transmitted to the ground, hopefully. So to do this, we used Arduino. And I apologize for my constant mispronouncement of Arduino, whatever. I'm going to call it Arduino. So I like Arduino mainly for its hardware abstraction. Once I start dealing with a microcontroller, I don't really care. I don't want to muck around flipping bits in a register to do something. I just want to have a function which does it for me. Arduino does this already. Digital write, for example, everyone knows that function. Pin number, state, done, it's great. And Arduino does this really, really well. There's also heaps of existing libraries. We used a couple of these, so particularly to talk to the SPI EEPROM. We had to modify it a bit, but it was still a good starting point. And the biggest thing that I like about it is one-click compile and programming. Click, done, it just works. There are some annoyances, which I'll get into now. So the GPS we're using sends out lots of data. We're talking kilobytes of data, semi-random intervals, and well, Arduino's hardware serial library has a 128-byte long ring buffer. We fill this up really, really quickly, and if we're, say, talking to the platform with an I2C command, often we'll kind of go around the ring buffer and we'll start losing data, which is really bad for us. So what we ended up doing was adding a set callback function. This is an idea that was floated at last Linux.conf actually by Thomas Sprinkmeyer. I don't know if he's here? Hi, thanks for the idea by the way. So this added a callback function. So this allowed us to override the Arduino's interrupt service routine, which is what gets called whenever you get a new byte coming in. And I ended up writing my own parser, which would kind of strip out the data that we needed and dump it into a swing buffer. So this is where we have 2 buffers and we switch between them. So one fills up, we inform our main loop that there's something to be done. The main loop can go and process that while we write into the other buffer. And this worked pretty well. So another part of Arduino that we ended up getting rid of was the bootloader. So the bootloader is mainly used to let you program an AVR via serial, so via USB serial or using on the Arduino Uno via the little 18 megabit USB to serial chip. We didn't really need this. We already have the ISP header, the in-system programming header on the board, so we figured we'd just use that. So if you're going to use it to program the bootloader, you may as well just program the entire chip using it. And Arduino lets you use an ISP. For example, I'm using an AVR ISP Mark II programmer to program sketches. It's just a 1-line change in the preferences file. Really, really simple. I use a similar technique on my balloon payloads where I don't want to spend the space to have a serial programming header. If you come to my talk tomorrow, you can find out more about that. So, things that can go horribly, horribly wrong. Well, there's the launch failure, of course. We're launching on a converted Russian ICBM, which is a pretty cool launcher. I'll show you a video of that in a minute. Now, it's had 17 launches. One of them's failed. There were 10 CubeSats on that launch. So, yeah, a pretty big failure, but it's not too bad. Other problems, radiation. So the effects of radiation and fallout. Not fallout, but anyway. We don't have much of a problem with radiation. Now, geostationary satellites are above the Earth's Van Allen belts and they're exposed to cosmic radiation, high energy particles that can do really nasty things to microcontrollers and CPUs in general. We're below the Van Allen belt. So the Van Allen belt traps these high energy particles, or at least most of them, and protects us. There is still the chance something really bad can happen. So for example, we could get a really high energy particle coming in and smashing through our flash memory on our microcontroller. Game over. Payload's down. The platform, as in the rest of the CubeSat, will keep on going. It'll say, okay, this payload's got a problem, we'll shut it down. The mission isn't a complete failure. If we get a bit flip in RAM, that can also cause problems. Now we have a hardware watchdog. So if we don't kick the watchdog every, I think it was 30 seconds in our case, our payload gets reset. which is fine. The platform also acts as a watchdog. If we don't respond to one of the I2C commands, we get reset and sometimes shut down. There are a couple of interesting conditions there. EEPROM failure. If, for example, we lose a page of EEPROM, what we do is we mark it as failed and we don't use it again. We also have checksums in our long-term storage just to make sure nothing's been damaged. If the EEPROM fails entirely, we can use the huge amounts of RAM inside the 80 mega RAID. So we can fit about 20 packets in the 80 megas RAM. So what we do at that point is tell the platform we need to send our data now, and hopefully they'll let us send data down. If they don't, well, we lose data, which is quite sad. GPS failure. This is actually quite a big one. That GPS device I talked about earlier has an ARM7 core in it. So if anything's going to fail, that's going to fail. It's got a little bit of shielding, a bit of aluminium. We could put a bit more aluminium over the top of it as well. That may help, that may not. There isn't much we can do about it. The GPS fails. Damn, moving on. Comms failure, uplink and downlink. This is actually a really big one. So the main downlink, well, there's two downlinks I should say. There's a VHF downlink on a ham radio band, 2 meters, at 9600 baud. Not very fast, but that should be pretty reliable. The other downlink is a 1 megabit per second downlink on 2.4 gigahertz. Now, what else runs on 2.4 gigahertz? Everything, yeah. There's one receive site, one ground site for the 2.4 gigahertz downlink. It's somewhere out in the field in the UK somewhere. They're not completely sure it works at the moment. They're having problems with that downlink. So if that doesn't work, we're going to be very limited in what kind of data we can get down. The other problem is the other downlink, the lower speed downlink. Again, there's only one ground site. So we have a small window to get data down each orbit.
Couldn't you open up extra downlink sites?
We can. There's one opening up in Adelaide, which I'm setting up. There's also an amateur radio project to start a whole bunch of downlink sites. That currently is in development. I think they're getting to the stage where they're going to start deploying it. If that's working, we'll be using it, which will be great. But at the moment, it isn't really there, but it's getting there. So I'm pretty much wrapped up. I talked a lot shorter than I anticipated. This is a NEPA launch. So the really cool thing is it's ejected from the missile silo using black powder. The rocket doesn't fire until it gets out. And off it goes. So pretty much late this year, YouTube's going to be launched from one of these. Any questions?
The ham radio downlink project, any more details about
I can't remember the name of it. It's used for a lot of different CubeSat projects, and particularly I think the FunCube project is involved with it as well.
Because there is that I'm not sure which frequency it runs at, but there is that project where they do GPS coordinate, like you drive a car.
APRS, you mean?
APRS.
We can't use that for this particular project. The downlink format is using the same packet format as an APRS. It's called AX25, but you wouldn't use the APRS network for that. Any other questions? Guy at the back.
Right. Will the CubeSat have any propeller in it for station keeping? Or
No.
Send and do a focus right?
It's got gyroscopes. That's it. Yep. Look.
Have you ever had any luck getting GPS receivers from Asia or Europe without dealing with ITAR, without dealing with the ITAR firmware restrictions?
No. Even if we could, we wouldn't be allowed to use it.
What about Linux?
Again, I think it's probably the same restrictions. So I think the same restrictions apply, and
Or from the Russians? Or
I really don't know. I don't know much about GLONASS.
GPS, right? So it's not going to be under ITAR, which is the US version.
Well, GLONASS is only single frequency, isn't it? Or is it dual frequency as well?
GLONASS, each satellite is on a single. It's weird. They do frequency mapping. They do CDMA spread spectrum, but they didn't trust themselves to actually get it all right. Frequencies, each spacecraft is on a separate carrier frequency.
Interesting. If the frequencies were far enough apart, that could actually be quite useful. I don't think anyone's done any work using GLONASS yet.
GLONASS, unfortunately, is not well maintained, and so
Yeah.
future dependencies on it is a great plan, but there are other global applications.
Galileo has potential if the problem is the EU is currently bankrupt. And I think they spent $4 billion on the first Galileo satellite and they actually didn't get anything. So Yeah.
If you want something that really works properly, it really has to be GPS.
Yep, it's all we can use.
So frankly, I'm still waiting for somebody to do what we almost did in AMSAT years ago, which was to build a completely open receiver design.
Yeah.
So there are USART-based GPS receivers, but they're very simplistic, and I don't think they're actually they wouldn't work for us.
I'd love to have a lengthy conversation about this as long as it's very much off the record.
No problems. All right.
I know too much about it.
All right. I think we better wrap up. Thank you very much.